Let us now understand what is law of conservation of energy, and this holds true in all scenarios. So whenever the energy gets transformed, the total amount of energy always remains the same. In the previous slide so far, we have seen that energy initially when the object was at rest, it had potential energy. You apply some force, the object starts moving, it acquires kinetic energy. But if I compute the total energy of the system, it remains the same. So if potential energy is more, kinetic energy will reduce. And if the kinetic energy is increasing, the potential will reduce. Look at the law statement. Energy can only be converted from one form to another. It can neither be created nor be destroyed. The total amount of energy in the universe remains the same. This law is valid in all situations and in all energy transformations. So whether I am converting that energy from one form to the other, let it be from electrical to sound, sound to light, light to electrical, light to mechanical, doesn't matter. The total amount of energy in the universe will be conserved. It would remain the same. Have a look at this diagram. An object from A is dropped to point B. Let's see what happens. At A, potential energy is maximum, kinetic energy is zero. When it is being dropped during that transition, the potential energy reduces and the kinetic energy increases. And when again it touches the ground, again it comes at rest, so the potential energy is gained and the kinetic energy becomes zero. So overall in the entire transition from A position to B position, the entire energy of the system is conserved, it remains the same. When we say that the total amount of energy in the system remains the same, let us have a look at some energy transformations. What do you see in the picture? A car engine. Car is producing, that engine is producing some kind of energy. What do you think would be its transformation? The petrol in the car, which possesses chemical energy, burns, it produces heat energy. That heat energy in turn drives the other machinery, making the car move. That is kinetic or mechanical energy. Look at the second picture. What do you see? A bulb? What do you think it has? Again, over here there is electricity that is supplied, which heats up a filament that converts or that emits energy in form of light, and we see things. Radio. What do you think is the energy transformation? Yes, a battery. If you're taking a battery, it would be chemical energy. If you're considering it connected to the power supply directly, it would be electric energy. Either way it's okay. So electric energy then makes the diaphragm move, which produces sound energy. So these are just few sample energy transformations. Definitely every time there is some of the energy that is used to do a particular work, that energy keeps changing from one form to the other. Now, so far we've been discussing about law of conservation of energy. What if I want to verify whether really does that energy is the total energy of the system remains the same? Now, this derivation, we will look at it. It is not as given as on the slide. It is not there in your book, but this is for your additional reference. Let us assume that an object of mass m has been raised at an height h. So total height from C to A or from the ground level to A is h. Let us consider case 1 when the object is at position A. Here the initial velocity u is 0 because the object it has rest, and thus its kinetic energy will be 0. What will be the potential energy? If you remember the formula mgh. So total energy, that is Ke plus Pe, remains as mgh plus 0, which is mgh. So in case A1, when the object is at position A, the total energy is mgh. What happens in case 2? Let us say that the object has now released from A and it covers some distance, and this is the transition phase B. Okay, it has covered some distance, say S, and it has acquired some velocity, say V. Now by using the third equation of motion, I know that v square is equal to u square plus 2as. Here v square is equal to, I know u is 0, no, and that s or that a acceleration is due to gravity, so I can now replace that a as g. Okay, so I know that v square is equal to 2gs. If you remember the formula for kinetic energy that we have studied, half mv square, plug in the value for v over here, v square as 2gs. What do I get? I cancel out this 2. What remains with me is m, g and s. This is my kinetic energy when the object is in the transition from A to C, is at B, at position B. Now have a look at the potential energy. Potential energy is mgh. Now over here the total height is h. From A to C it is h. Okay, so definitely some distance has been covered. It is not at C, it is just somewhere in between. So at that time I consider this is as S. So my height will be h minus s. Now if I plug in the values for ke and pe, what I get is mgs plus mgh minus mgs. So it goes off, what I have, total energy is mgh. Thus in the second scenario, when the object is at position B, what I still have that the total energy of the system is mgh. Let us take case 3, when the object is at position C, where it has just touched the ground. Again, just touched. Okay, so what I have, the potential energy is 0. So u is equal to 0. Initial velocity started with 0. Distance, now it has covered the entire distance, that is h. Okay, total height, and it has acquired some velocity v. Again I am using the third equation of motion, v square is equal to u square plus 2as, and I plug in the value for u square as 0. What I get is v square is equal to 2gh. H, why? Because the total distance is h. Now, and yg because it is acceleration due to gravity. So now what do I have? Kinetic energy is equal to half into m and v, that is 2gh, which is mgh. So in either scenario, if you have a close look, everywhere you have the total energy remaining the same. So whether the object is at point A, it was mgh, at point B, it was also mgh, and at point C, again mgh. Thus I say that the law of conservation of energy holds true in all the three scenarios. So the energy was just getting transformed, potential to kinetic, kinetic back to potential. And if you remember, it also says when the potential was maximum, kinetic was 0. The ball rolled out, the potential energy decreased, the kinetic energy increased. Just before touching the ground, the kinetic energy was highest, and the moment it touched the ground, it came to rest, the potential energy again is highest. Thus, the law.